You're saying a second order derivative is going to become fourth order derivative?
No, I mean, you said the derivative, the expansion has only 4 terms.
Which one only has 4 terms? You're saying this one?
No, the partial x squared.
Oh, you think it only has 4 terms instead of 8? So the reason it has 8 is that when you substitute this into partial u partial x, the first component of partial u partial x is going to split into 2 terms because of the derivative to c. You're going to get second derivative of u with respect to c times partial c partial x plus the first order derivative of u to c times the second derivative of times the derivative of partial c partial x to c. All right, because this number is this partial derivative is comes from the mapping. If your mapping does not have a constant Jacobian, then this Jacobian can potentially depend on c, so you may have additional terms. Yeah, don't miss these terms. Otherwise, you are not solving the Poisson's equation in the physical domain. You are solving a different equation. All right. Any other questions?
How do you come up with the mapping function?
How do you come up with the mapping function? That's a very good question. That depends on the domain, and I don't have any uniform answer to that. So there is no fixed procedure for you to come up with the mapping function. You need some creativity and trial and error to do that. Any other questions? Yes?
To clarify, the mapping function can make the space nonlinear, right?
The mapping function can make the space nonlinear. What does a space being nonlinear mean?
Sorry, the actual PDE you're solving in the computational domain, it will make it nonlinear if you choose.
If I choose some mapping?
Yeah.
Actually, the answer to that question can be seen from this equation. If you look at this equation, is this equation linear or nonlinear? It is linear, because all the parentheses should not depend on u. They are going to depend on the mapping, and they are all the parentheses are nonlinear functions of the mapping. In that sense, you are right. But none of these parentheses depend on u. So the resulting equation is a linear equation in u. All the nonlinearity has to do with the mapping itself. You still get a linear equation. Right? The difference between linear equation and nonlinear equation is looking at the solution u. Any other things not important. Good questions. Yes?
So in your mapping to your computational space, you can set the grid points sort of arbitrarily wide or narrow, and there are infinitely many maps. So
Yes.
how do you choose how big the map or the discretization to use in your computational space?
Okay, the question is, I can make the spacing in the physical domain arbitrarily narrow, arbitrarily wide. Is that the?
In the computational domain. Like you mentioned in your physical domain, and then when you map it to your computational domain, you can put them as far as close as possible, so as long as you're coding still like invertible.
Right. Okay. So the relative spacing between the computational domain and the physical domain, right?
Yeah.
That's also a very good question. That the choice of that you're going to see depends on what is the required resolution of the function in the physical space. So we have seen the other day that like when you have a very oscillatory function, you need smaller delta x for the truncation error to be small. If you have a smooth function, maybe you don't need such a small delta x. So a good mapping, the ideal mapping should map the physical space into the computational space, such that the solution U in the computational space does not have finer features in one area than another area. Of course, that's easily said than done, because in a lot of cases, without solving for the solution, how do you know how the solution behaves? But in some cases, you do know. For example, in this airfoil example, we know that closer to the airfoil, there is what's called a boundary layer, where the solution varies very quickly in the normal direction. So we usually construct a map such that the resolution in the physical space near the wall is much finer than the resolution in the far field, for example. So again, there is no procedural way to tell you how to construct the mapping so that it's ideal. A lot of these are application dependent and also depend on your knowledge, your prior knowledge to the problem.
Do we always keep the uniform space in the computation domain? So
Do we always keep
non-uniform one? We could have a uniform one in the physical domain.
Yeah, do we always have a uniform grid in the computational space? Not always, but it's preferred in finite difference. As you probably can figure out in last lecture where we used Taylor series to construct finite difference schemes. It's probably not a good idea to do the same thing at every grid point, right? So if at every grid point you have a different grid spacing and different on the left, different on the right, you have to do basically the Taylor series analysis, solve this matrix equation at every grid point to figure out what finite difference scheme you use. I mean, you can do that, but like it's not. I mean, most people in most practice just feel it's much easier to have a uniform mesh in the computational domain. Yes?
But having different delta x and delta y is easy for finite difference, right?
Oh yes, having a different resolution in different directions is much easier, yes. That's right, because then your finite difference approximation does not depend on which grid point you are on. It's always the same delta x, it's always the same delta y, although delta x is not equal to delta y. All right. Any other questions? Uh-huh.
One more question.
Yes.
In the computational domain, delta x is fixed between all the points.
Yeah, in computational domain, delta x is fixed across all the points.
Do we have to do the math in such that the distance between points in each axis in the physical domain is also equal?
No, you don't have
We
to.
have to have custom delta for every point.
Well, in the physical domain, there is not a good definition of what is delta x, what is delta y, right? So if you map a horizontal line or a vertical line in the computational domain to the physical domain, like these lines are going to be curves. They are not going to be straight lines, right? And you can see from these examples that the spacing between adjacent points are wider here than here. So
We're going to use these deltas though, right? We're only going to use delta x and y when we solve the PDE.
oh, in solving the PDE, in the discretization, we are going to show that we discretize in the computational domain. We do not discretize the PDE in the physical domain. We derive from the PDE in the physical domain to what different PDE we need to solve in the computational domain. Then we use finite difference on the PDE in the computational domain. The reason it is called computational domain is this is the domain where we do our finite difference computation. Does it make sense? Any other questions? Now let's take a short break and come back to how do we actually do 2D finite difference discretization.